So if you haven't yet done Wednesday's in-class exercise, then you should probably delay watching this video. So the video is pretty short. You can watch it between class Wednesday and Friday, but I really want you to try Wednesday's in-class exercise before you watch this video. The reason is that at the end of class, I posed the question, which is, what's an access pattern that will make LRU behave abominably? And in particular, we're looking for an access pattern where LRU will give you exactly 0 cache hits. And it turns out that that access pattern is remarkably simple and common. And that's something to be aware of. So it turns out the access pattern is just iterating over the same pages or objects or cache lines when the set of objects is just larger than the cache. So let's see what happens here. So I've initialized our cache with A and B, and we're now on the third axis C, and we see that it's a miss. So what are we going to do? If we're using LRU, we look backward in time and we say, oh, we need to evict A. So we evict A, and then we put C in there, and that counts as our third compulsory miss. We say, great, now let's go on. And then we move to the next item, and it's like, oops, it's A. I just kicked that out. Bummer. Well, what do? I look back in time, B needs to get kicked out. So I kick out B, I put in A, and that's actually a capacity miss because if my cache were larger, A would still have been in there. So that's a capacity miss. Now you might see where this is going because I look at B and it's like, oh, I just kicked that one out. And so now I replace C, and lo and behold, the exact same thing happens when I get to C, is that I look back and I can't find that. And so now I have to kick somebody else out. So it turns out that when the set of objects you're touching is just bigger than the cache, LRU produces terrible performance and gives you a 0 hit rate, which is awful. All right, so what's the best thing we could do here, and is it practical, right? LRU did the wrong thing like every single time. Well, let's see what we really want to happen. Like if we were smart and could use Biloti's algorithm, like what would we be doing? So once again, we've set up, we're trying to access C, and A and B are in the cache. And I say, well, now I'm going to look forward in time and realize that I don't want to evict A, I'm going to evict B instead. So I get rid of B, I put C in there, and I take my third compulsory miss. But now when I move to A, it's still in the cache and I get a hit. And then I move to B and now I have a miss. And we can't quite look far enough in the future to really know what's going to happen. But what you might realize is that the ideal thing to do here is to kick out the object I just touched. So in this case, I want to kick out A. I now take the miss for B, but when I move ahead to C, I get another hit. So this policy is actually called MRU. It's most recently used, right? And it turns out that when you're iterating over a set of items or an array that's just too large to fit in the cache, MRU is actually a really good solution. And if you think about, I mentioned maybe briefly at the beginning, you could have like first in, first out, or last in, first out. MRU is really a last in, first out, right? So the last thing I put in the cache, that's the thing I'm going to kick out because that's going to leave the things that I'm going to hit next time I come around. So by looking at MRU, which was that last algorithm, we've really looked at both MRU and LIFO. So let's look at one last algorithm, which is FIFO. How does that perform? So now what we'll do is when it comes time to evict, we're going to look and see which item has been in the cache the longest or was loaded earliest. And I'm going to kick that one out. So this is the same sequence we worked with in class. And what you'll see is we've started at the point where we've loaded the cache with A and C. We've taken a bunch of compulsory misses as well as our hits. And now we say, I need to load item B. What am I going to do? Well, now we look back and we say, well, the thing that's been in the cache the longest is A. So let's kick A out and put B there. And once again, that's our last compulsory miss. So we move to the next access, and that's B. So that's a hit. And then, yay, we get another B, and that's a hit. But now I move forward and it's like, oops, I really wanted A in there. All right, well, I'm going to look backward in the cache. Which one of B and C has been in there the longest? Well, it's C. So let's kick C out and put A there. We took a capacity miss for that. But we go on, we get another A, and that gets a hit. And this time we get B, and that's also a hit, and I don't take another miss until I get to C. So FIFO is a little different than LRU, right? It really is how long you've been in the cache, not how long since you've been accessed, but in some ways it can sometimes be easier to implement. All right, so if we count up our hits and misses, we see that we got a hit rate of about 7 out of 12, and that was comparable to what LRU gave us. So at the end of the day, there really is no perfect cache replacement policy. LRU is often just fine. It is perhaps the most commonly used one. LFU, least frequently used, is sometimes a little bit better, not always. But there are particular patterns that you might want to be alert that they might happen, like this iterating over a big item. And in that case, you might want to detect that and use something like MRU. So for anything other than the optimal workload, the optimal algorithm, Bilottes, which is totally impractical because I don't know about you, but I can't predict the future, you can construct an adversarial workload that will make the policies perform badly. And so this is all a sort of an optimization game, which is picking the best one for the workload you have. Unfortunately, you don't often get to change your replacement policies based on the workload, right? In software, you could be a little adaptive, but in hardware, you're kind of stuck with whatever the hardware gives you.